Okay, let's get going. So before we actually start today, I just want to do a quick little overview of the content that needs to be sitting in the back of our heads as we engage with these questions. So in the last lesson, we spoke about what are called the converse theorems. The converse theorems help us prove something is a cyclic quad, or help us prove something is a tangent. So just to remind you what a cyclic quad is, if we have a quadrilateral, if we prove it's a cyclic quad, we know we could fit a circle through it. Okay, that's not a very good drawing. But basically, if it's a cyclic quad, we will be able to fit a circle through it, but it doesn't mean we have to visually see it. What we check is if something is a cyclic quad, then the opposite angles will be supplementary. The other way of checking is if we have an exterior angle equal to an interior opposite angle. And then the third way to prove something is a cyclic quad is to show that the line segments subtends equal angles, or that these two angles are the same. And we call that like converse angles in the same segment, converse exterior angle cyclic quad, converse opposite angles or supplementary. Give me a thumbs up if you remember that from the last lesson, that there are these three ways. I just want to point that out so that it starts to sort of stick in your memory. Those are the three ways we look to see and prove something is a cyclic quad. And if we are going to prove that something is a tangent to a circle, what we need to prove is the angle between a line and the radius is 90. So if we have a line and then we have a radius, our radius has to go with a circle. So if we have a line and a radius combining, if that angle is 90, then this thing over here is a tangent. And that's called converse tan radius theorem. And then the converse for the tan chord theorem just says if the angle between a line and a chord is equal to an angle in the other segment. So basically, if this one over here is equal to this one over here, then this line will be a tangent to a circle. Okay. So give me a thumbs up if the converse theorems for tangents, you feel like you've seen that before at some point. Okay, so that was what we spoke about a little bit in the last lesson, but we need to practice more questions like that. And that's what we'll do today. But just before we get started, I just want to show you that often I talk about the bins of theorems. And so if we look at this picture over here, this shows us the theorems that deal with circles and the center. So circles and the center. So here we have the line from center perpendicular to the chord. Probably the most common one is that the angle at the center is twice the angle at the circumference. We have the angle in a semicircle, and then we have equal chords, equal angles. So that's the one collections of theorems that I like students to think about. What are all the theorems that do with the center? And then what we've got is we've got circles and cyclic quads. And there we can see here our cyclic quad theorems over here. So angles in the same segment, opposite angles of a cyclic quad, exterior angle. And then the last group of theorems we need to keep in our brain is circles and tangents. And so here we have the tan radius theorem, we have the tan chord theorem, and we have tangents from an equal point. And so really all we need to do is get better at using these tools. And so, yeah, we can do that. So somebody's asked to go up to take a screenshot. So all of these things are in the notes as well. So I don't want you to obsess about memorizing. The best way to learn it is by doing questions, which we will do. But I just wanted to give you an overview as we got started today, because I know it's a lot. And so it's nice to reinforce the content. Okay, but enough of me talking. It's time to rock and roll. So let us start. Let me move all these other questions I have got ready out the way. And I will zoom in. And you are going to start by helping me solve this question. So it says here, in the diagram, a circle is drawn passing through A, B, C, D, and E. Let me make this a little bit thicker. A, B, C, D, and E. We can see A, B, C, D, and E. The two tangents at B and C meet at T. So they're kind of saying, look, T is here, and here is a tangent from here, and here is a tangent from here. And they're from the same point. It says BEC is X. Now let's go and find BEC. Oh, there we go. BEC, so BEC is X. And it says D is Y, and angle D is down here. All right. I want you to try and find B2. Oh, it's sorry, one more thing. It says find the following angles in terms of X and Y and give your reasons. So what I want you to do is let's try and do these first two first. And then once you've got your answers, you can put them in the chat. So that's how that goes. Where is B2? Find it on the drawing. So Mbali and Zanele, no problem. Okay, so let's have a look. What is B2? So B2 is up here, and we have to find what this is in terms of this angle over here, which is X. So, or in terms of Y. Either of those things are fine, because it says in terms of using X and Y. So what I was thinking is, what theorems are involved here? What do we have that we can use? So we kind of know that this and this are going to be equal. Okay. And that's going to be because of tangents from a common point. So we know that, let me get a bigger pen to write with. I think I've zoomed in too much. Oh my goodness. So we know that BT is equal to CT, and that's tangents from common point. What we now know, I suppose we could say that this one over here is going to be equal there. But what we want to do is connect it to this X over here. How do we connect that to the X over there? How do we connect C4 to the X over here so that we can write B and 2 in terms of something? So it could be exterior angle in cyclic quad. So my cyclic quad here would have to keep going, and it would be equal to, so Morgan, I think that this angle over here would be equal to that angle over there, but that problem is I need just the X part. What about if I say, is this a tangent? Isn't this a tangent? I think this is a tangent. And this is a chord. Isn't this a chord? It looks like a chord to me. Are you following my thinking here? Yeah, so if that's the tangent and that is the chord, that's the angle that I'm interested in. This is going to be, it feels like this one over here is going to be equal to that one over there. So what I think I'm going to write, let me just switch back to the right pen here. I'm going to write that C4 is equal to X, which is by the tan chord theorem. And then I'm going to say C4 is equal to B2 because angles opposite equal sides. And then I'm going to say, therefore, B2 equals X, because I know from that relationship. So this is going to be equal to that, and that's equal to that over there. And you could say because C4 is equal to B2. Yeah, you have to, because you've shown that combination there. So this to this, and then this one equals that one. Therefore, B2 equals X. Give me a thumbs up if you followed my logic for this first one here. Okay, let's try and find C4. Oh, wait a minute. We've solved for C4 along the way. So we did this one already. C4 is X by the tan chord theorem. So let me do it again, because I think I've lost some of you. So let's go back and get rid of all the messy stuff. So the key idea, it looks like, is to take this tangent and see that there is a chord there. Let me make it a bit better. Okay, so first of all, you need to see that. Now C4, this chord BC, subtends an angle over here, which really then shows that this angle over here is equal to that angle over there. But because this is a tangent from a common point, we know that that and that length are the same. So therefore, C4 will be equal to B2. Or, they're both going to be equal to X. So another way of writing this is to say that's X. This is X. Therefore, that is X. And so we've answered B2 and C4. So that's what I've used to write it up. Give me a new vote after that explanation, or give me a happy face if that helped a little bit. Give me a happy face. Give me a happy face if it didn't help. We don't need to rush, so we can just take our times. Okay, unhappy face. Okay. So what I want you to do is, if you're feeling unsure, don't worry. You can re-watch this recording, and then you will see it gradually over time. But let's go to T. If we wanted to find T, where is T? First of all, on the drawing. I think that T is sitting over here. What do we think T is in terms of X and Y? Remember, this question we often, when they say this in a test, they're saying use the value of X and Y. Now we know X and Y are these angles down here, so we're trying to link them. Now we've already got that this is X and this is X. What is T going to be? Put it in the chat if you feel like. So T is not going to be X. There are X's in the neighborhood. Yes, it's going to be 180 minus 2X. And what's the reason going to be? Who feels like they know the reason? So T is 180 minus 2X, and that's because sum of angles in triangle. 180 minus 2X. Yeah, that wasn't so bad. Okay, we've got T. Now let's go to A. I want to give you some time to find what you think A is. ask yourself, what shapes are in here? What shapes are there that you can see or connect? Is there a center of the circle? I don't see any centers of the circle. What I do see are tangents, and I do see cyclic quads. So I'm thinking, what theorem can I play with that deal with this? Okay, now, we know that, what do we know so far? Angles in the same segment. Can you say isosceles triangle for T? The official reason, Bomb, is to use angles opposite equal sides. There's no official reason that says isosceles triangle. I mean, teacher will probably be okay with it, but I prefer you to use this language over here. Okay, so what do we need to do? We need to find a way to connect, okay? We need to find a way to connect to the T. So what are we going to have to do then? Where is a cyclic quad here? Let's have a look. Where is angle A? Okay, this is sneaky. Which cyclic quads? Name some cyclic quads for me. In this drawing, what cyclic quads are there? Oh, Morgan, you're on the money. AECD, AECD, yes, well done. So can we see, and I want to point this out because honestly, it almost caught me. If you look at this thing here, even though it's sort of scrunched up, it feels to me like this is a cyclic quad. And what do we know about opposite angles in a cyclic quad? So you're right, we've got the EDCB one, but the blue one is the one that I'm very focused on. And so now I want to ask you, if you know this is Y, isn't this the opposite angle in the cyclic quad? Yeah, they're supplementary, exactly. So what is the angle A going to be equal to? It's going to be 180 minus Y, and the reason is going to be opposite angles, cyclic quad. Sorry guys for my writing there, I'm just squeezing it in. But this is going to be 180 minus Y, because opposite angles in a cyclic quad add up to 180. Again, let's do another vote. Thumbs up if you got that, thumbs down if you didn't. All right, now the last one in this question, what is B1? What is B1 going to be in terms of X or Y? What is B1? Where is B1? B1 is up here. And so what is B1 going to be? Well, it looks to me like there's a nice butterfly that can help me. And what is the relationship between these? Are the same angle. So this must be 180 minus Y. And the reason is angles in same segment. And so we know this is 180 minus Y. So as we look at the different types of questions you can get asked in circle geometry, sometimes we have to find things in terms of X and Y. And then we don't have to worry. It's a little bit harder than saying find 3 angles equal to 40, but it's still the same basic idea that you're finding equivalent angles. Okay. Are there any final questions on this one before I move on to the next question? You did well there, because I'm definitely giving you harder questions now. And so if you feel a little bit of growing pains, don't worry. It is part of the process. Okay, well then let us move to the next question if there are no other things right now. So let's have a look here. To what, let's leave this one. Let's go to one that has a cyclic quadrilateral thing involved. So let me skip that one and we're going to start on this one. Okay, so here is your question. You are given the following drawing and take a moment to introduce yourself to the drawing. How would I introduce myself to the drawing? I'd probably read through it and just highlight any key ideas. So QS is a diameter. So QS, now that drawing is, it looks a bit skewed. It's actually completely straight here, huh? So I don't want you to get confused. That's completely straight if it's a diameter. It says AU is a tangent. Notice how my brain is loading up the information that I need. And it says PQ is parallel to UO. Now, where is P? Oh, wait, PU, UO. Oh, here we go. So that one is parallel. And you can see that little arrow there. The colors help my brain. I really think using some highlighters can be helpful. Okay, find me 3 other angles equal to X. At the moment, X is this angle up here, P4. See what you can do. Okay, Rosario, wouldn't P1 equal to X? Maybe. I have to go do some investigating with you guys. Let's have a look. I don't know if I would go with A. What I was thinking is, if this is a tangent, right? If the yellow bit is a tangent, normally the angle between the tangent and the chord, so let's say like that angle, I was thinking, remember this is a straight one. I was thinking the P4 and S could be involved. Because it's, I know that this thing is a bit off, but like basically it's the tan chord theorem. Huh? So like this one equal to that one. Oh, I see. Mdudu agrees with me. Okay. So we would say, you can just say angle S is equal to X, and that is going to be the tan chord theorem. So we know this is an X. Now, what else could we possibly find? We need 3 other angles equal to X. Q2, there's Q2. I don't know if I would go with Q2 because I don't see a clear, I know there's the diameter. So, I mean, that could be 90, but I don't think that helps yet. What other colors have I not? Oh, well, there's a pink thing, which could be helpful, I guess, maybe. Well, what other things could be equal to X, do we think? P2, yes, P2. How do we know that P2 is equal to X? So I agree, P2 is equal to X. What is the reason going to be? It's got a lot to do with this thing over here. So I think the reason is, and Bom agrees, it's radii. So these two have to be an equal length because they are radii. So we know that this one over here is going to be an x. Now we need to find one more x on the drawing. Why can't we say T3? Where is T3? Dudu, let's have a look. Where is T3? Because here's T. I don't see any numbers around there. So, and then that's a radii, but we don't know what that angle is there. O1, O1, we don't really know that one either. Off the top of my head, no. Okay, I'll give you a hint. What do the pink lines do? What do the pink lines do? They're parallel. What shapes do you know about that deal with parallel lines that maybe could help you? There's Z, but the problem with the Z is the Z would be here. What do you guys know about the F shape or the F shape? Wouldn't it be that this angle over here, this X, would be equal to this one over here? What's the name of that relationship called? Or that theorem? Because you've got parallel lines. Often we talk about the F shape and we speak about the U shape, or we speak about the N shape. I think this is corresponding. Yeah, because you can see it's the F upside down. So we would say angle, to be completely correct, we should say, let's say S, wait, no. We'd say OUP, so OUP is equal to X, and that is going to be corresponding, right? Corresponding angles, and we know that PQ is parallel to UO. And so we know that is X. Okay, we're almost at our break time. I just want to do this last thing here. Okay, so we've got X there, and so on. Last question before the break. Prove with reasons UPOS is a cyclic quad. Now, if I want to find where UPOS is, UPOS. Now, just because you can't see a circle going through that blue thing doesn't mean that it can't be a cyclic quad. You could maybe fit a new circle through this. Can anyone tell me how we're going to prove, apologies for my scribbly writing, I was just trying to show you this bit here. How would we prove that UPOS is a cyclic quad? From what we thought about earlier in the lesson. Any ideas? Can anyone spot anything? Maybe you want to put your hand up and you can tell me audibly. U equals S. Yep, Ndudu. Yep. So we can say that UPOS is a cyclic quad. And the reason is that we know that angle S equals angle U equals X. And that's what we've proven. And then we can say, therefore, UPOS is a cyclic quad. And the reason, so I suppose I can, let me remove this. I would normally say the angles I'm talking about. So UPOS is cyclic quad. And the reason is converse angles in same segment. So we're showing that the angles are equal in the butterfly, and therefore it must be a cyclic quad. And so the key thing is to recognize that this angle over here and this angle over here are the same. So it's converse angles in the same segment to prove it's a cyclic quad. Give me a thumbs up if you followed that. Give me a thumbs down if you didn't. Okay, awesome, 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 awesome. I've pushed you a little bit further than normal, so it's time for a break. We are going to take a break now. So I want everyone, cameras on, stand up. It's time to free our minds a little bit. You've done well. You've done well. Okay, let's start with some deep breaths. So we're going to start and just go. One more deep breath. Okay, let's do one more after this, and make sure you're breathing through your nose. Okay, so hopefully you can feel the oxygen flooding your body. Let's start with a bit of a shake. So just shake your arm quickly, shake your arm, shake each leg. And then let us start with a little stretch, like a tricep stretch to, if you've been hunching your shoulders forward, we can just stretch them out quickly. And then over to the other side. Oh, I feel tight, my shoulders. And then swing your arms like you're an Olympic swimmer, just, and then I tell you what, let's do some of those small circles just to go like that. And then as you're going into it, let's make it bigger circles. And then change direction. So you can go with big circles forward, like you're doing the butterfly. And then smaller circles. And then let's do some twisting. So we're just turning from our hips a little bit at first. And then as we feel more relaxed, we just start to extend our body. Oh, we can hear clicks. Okay. And then last exercise, just to get the heart rate and the blood flowing, we are going to do 20 or so air skips. So we'll start in 3, 2, 1. Let's go. Halfway. 5 more. 1, 2, 3, 4, 5. And that is today's exercise and brain break. Let me see if I can move. Oh, did I go to the wrong screen? I did. Let me. Okay. And Kia, can you see my screen now? I'm having some technical issues. Can you see the Mass 24 questions now? Okay, let's just do one Mass 24 question today. So can you make 24 using the red card? That number is 9. It's not a 6, it's a 9. So you've got 9, 2, 5, and 3. Can you make 24 using that card? Who has some ideas about how we can get to 24? So 9 times 3 gives us 27. Yep, that's a good place to start. So 9. So 9 times 3 gives us 27. We've used this one. And then, oh, Excited said 5 minus 2 is 3. So we've used the 27 and 3. And Sadiq, oh, you used another way. Yes. Okay, so 9 times 3 plus 2 minus 5. Yeah. Or you could say, I think I like that. 9 times 3 gives you 27, minus 5 gives you 22, and then plus 2 gives me 24. And there's a number of variations I can see coming through in the chat, and that's how you would get to 24. Okay, well done, everyone. That was a good one today. I like for a red one, it was a bit of a toughie, but not so hard that, you know, it broke our brains, but still nice. Okay, let's finish today with a couple more questions. So let's start with this one over here. Okay, so let's have a look at how we can do. Let me actually make it a bit bigger so it's easier to see. So oh, it's not working. Let me zoom in a bit. Maybe that's the problem. Yeah, okay, that's the problem. And let me make this a bit smaller. Okay, I'll put that there for now. Okay, so step one, it says here, TD is a tangent to the circle. So TD is up here. No problems with that. And one of the techniques I really want to kind of like help you guys to think about is, if you take a moment to introduce yourself to the question, it becomes a lot less scary. So I know that there's a tangent, and that tells me be aware that any theorems to do with tangents could be involved. I've then got AD parallel to BC. Now, they haven't actually labeled that. So let me make sure I do that. There is AD and there is BC. So I need to remember that, because when I have parallel lines, I have things like corresponding or alternate or these types of angles that can be involved. But my brain forgets that. And so it's important that if they haven't put it in for us, that I put it in for myself. So that's that bit. TBS is a straight line. It says WBT equals CBD. Now you'll see that there's a dot there and a dot there. And even if you want to, you could say, well, that's X and that's X, because they're both the same. And often when we have like, you know, you could just say let WBT equal X, and then it's easier to kind of let them run around the thing here. Okay, so the question is, can we prove that BWTD is a cyclic quad? Now, what are the three ways we have of proving something's a cyclic quad? It is either opposite angle supplementary, exterior angle equals interior opposite, or if the butterfly theorem, if the butterfly shape has two matching angles, or the converse angles in the same segment. I want you to go hunting and see what you can find in the drawing for me. And I suppose we should also highlight what BWTD is. So BWTD, so that is the shape that we are trying to deal with. Okay, so we know the pink quad is where we are playing. We need to find a way, BWTD, okay, what can we do? Well, if we could show that this angle over here was equal to that one, that would do the job. Or if I could show like this one was equal to that one, that could do the job. So there's a couple of ways, but we need to go look for information. B3 equals D2. B3 equals D2. I don't know what would your reason be. I don't think that's the case. B3 angles in the same segment. B3 equals D2. I don't know if I would say that, because here's that one and here's that one. That's not angles in the same segment to me. But maybe could we say, what about the tangent up here? So could we connect the tangent to, at the moment, we know these two things over here are x. Could we connect one of those things to the tangent up there? So if we look at this, what do we know about the tangent theorems? We're either going to use tangents or cyclic quads. The cyclic quad we have is A, B, C, D, but it doesn't look very helpful at the moment. So I was thinking, can I use this tangent up here? Maybe I should get my yellow highlighter out. Oh, wrong color. So can everybody see the angle D1? What could we link that to? What could we link the angle D1 to? So I was thinking, couldn't we get, well, B1? I was thinking, isn't it going to be B3? Like if you look, right? So if you go on your little journey, so here's your tangent, right? There's your tangent. There's your chord. The chord is the base, or you say that this chord DC subtends another angle, and that other angle that it subtends is down here. So I was thinking that this one over here has to be X. Give me a thumbs up if you understand that this D1 up here has to be X. So what I'm saying is the yellow one is a tangent. It says to me TD is a tangent. Okay, so TD is a tangent. Notice how it makes a chord here, and then that chord has like these two arms. The one arm stretches down like that, and the other arm stretches down like that. And what's between those two arms? It's going to be the X. Maybe I can zoom in even more and you can see it a bit more clearly. So all I was, oops, sorry, I think I've broken, I've broken my computer's brain. Let's give it a second to recover. Draw. Okay, it has got angry with me, so let's give it a second. But why is that helpful? So while I try to deal with the thing there, why is that helpful for me in finding the proving that BWTD is a cyclic quad? I really want to point you to these two angles. Why am I highlighting the green? Why am I highlighting those green things there? What does that allow me to do? So while you look at that, I'm going to write this up. I'm going to say angle D1 is equal to B3, and that is the tan chord theorem. Okay. Now, can you see a butterfly that has wings where the greens are the matching things? Yes. So you can see, because of the fact that, and you proved earlier on, you know that B1 equals B3 equals X, and that was given, right? So at the very beginning, they told us that B1 and B3 were the same. You then showed that D1, okay, is equal to B3, and then therefore you know that D1 equals B1 because they both equal X. You've shown that. But now, because of that, therefore, what do we have? BWTD is cyclic quad And the reason is converse angles in same segment. Okay. Now, I think I might have lost a few people there, and I don't want to overdo things, but can you see that basically I started by saying this is the same as this. I'm going to make them both x. Then I said this one is equal to this one. And because this one is equal to this one, and these are equal, the two green ones must be equal. And then I said I can see it's in a butterfly. That's why I'm using that. That's a tough question, but give me a thumbs up if you followed that. Give me a thumbs down if you didn't. Don't be shy. It's fine if you didn't follow. It's not a problem. Okay. For those who struggled with that question, I want to say, come back and look at the recording. It will make a bit more sense to you at that point. Okay. Even if you're feeling a bit like, whoa, 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 that's not a problem. We're just going to pause today on that type of question because we don't want to overwhelm ourselves in terms of what we're doing. So let me find one more question just to, okay, let me just leave this thing quickly so that it comes back. Why is it being so difficult? Sorry, everyone, for the technical glitches. Done that. Eventually, it will figure out that I am. Let's do this one just to finish off today. So I hope that you can see the drawing through all the bits of mess on the screen. Find me, let's just finish with 6.1 today. Can you find me three other angles equal to 80? Just find me three other angles equal to 80, and then in a moment this will clear, but until it clears, just give it a go. I don't know why it's being so difficult. It doesn't want to actually. So you're right. The first one is that R1 is equal to 80. And what is the reason going to be for R1 equals 80? It's going to be angles opposite equal sides. So we know that this one over here is going to be 80. What else could be 80 in this drawing, if you can see through all the clutter? Is there a butterfly here that could help us find an 80? Yep, R2. So R2 is matching. Oh, wait. You know what? It's not R2, everyone, because look, it has to be this whole thing, and the 80 has to be, so we can't be R2. No. Oh, I figured out a way how to get rid of the stuff there. So it's not going to be R2. What else do we have? We know that is, in fact, let me put the answer up for you here. So S1 would be equal to, how would I get S1 and S3? Oh, okay. So what we have here is that this one over here is the exterior angle of a cyclic quad. And so they go together. So S1, S3 would go together. We'd also have this one over here be 80. And then what is the final one? S1 being 80 would be angles in the same segment. Yes, S1 equals 80. Yep. Oh, that would be matching this one down here. Yeah. Okay, so there's a couple of ways we could do that. We have this one over here is 80. We've got this one over here, and we've got that one over there.